Yeah, I'm Curtis Villemizer for those people who don't know me, and I've been sort of involved in, the NSFnet, something that Bill might remember, and at this point I'm with Avicii. I had done coding earlier and then gone into operations, and now I'm back into writing code. What I'm talking about here is just about convergence techniques, or about really the impact of network architecture. And here on the slide I just put architecture. What I mean there is network architecture, like do you use areas or not use areas, as opposed to router architecture. Do you have a bus versus a toroidal mesh or something? That's not what I'm going to be talking about. And then I want to talk about algorithms, but not get so technical that this turns into a SIGCOM. Page up doesn't work. Page down. Okay, page down. I put the extended abstract on there for the benefit of the people who will be reading this. I thought before the meeting, although they weren't available before the meeting, the slides, or after the meeting for the people that either didn't attend or whatever. The convergence has changed over, and the notion of quality of service has changed over time, and Dave alluded to that in his presentation. And I'm not going to go all the way back to 1990, but in 1995, I think we had about 40,000 routes. I don't remember the numbers on Dave's slides to get the more accurate numbers. And convergence was occurring in typically like 1 to 3 minutes, although there were some networks in which they had stability problems, and convergence could take like 2 to 3 days on a really bad time. By 1998, we didn't have the 2 to 3 day convergence anywhere, and the 1995 problems were really sort of a short-term thing. They had to do with implementation problems in addition to what would be considered to be kind of a really dumb network architecture, which was to build a full mesh over ATM, which the provider that did that kind of learned that lesson and has confessed that it was a bad idea. At this point, the range of convergence, and here I'm talking about where a link changes or a router goes down, and all of the BGP routes are in there, not just sort of the IGP routes are back, but the whole BGP route table is correct. Ranges from, depending on whose router and everything, 1 to 5 seconds up to 3 minutes, if everything goes right. And a lot of routers have been moved to the edge, are still running full BGP, and they actually do take 3 minutes to update the full BGP table. So the state of the art is not wonderful, although we have quite a few more routes than we did before, and the number I'm seeing providers are telling us that they have on the order of 250,000 unique routes, because they have the global routes and they have their own internal routes. That's sort of on the high side of what we've been told. And my comment on quality of service is that in 1995, a claim of we have good quality of service was we suck less. Some people will remember that from past NANOG. Just for a hypothetical, just for a scaling discussion, we'll talk about 250K unique BGP routes, and we won't go into how many instances. 1,000, and everything is just powers of 10 just for the purpose of discussion. 1,000 node core, either a full mesh or 10 links per router on average, and that's just so that everything's a power of 10. And if you're doing areas, 10 areas with 100 nodes per area. Again, this isn't anybody's network. This is just on the scale of some of the tier 1 ISPs. Whether they have 40, 70, or 120 routers doesn't make a whole lot of difference. And we're going to consider two cases. One is where you run BGP with IP forwarding. In other words, you just have an IGP only. You don't use any MPLS. And the other case is where MPLS is used for traffic engineering. I'm actually not going to talk at all about the scaling of LDP, possibly because I don't know that much about it, but I haven't thought that much about LDP. And I don't want to get hung up in the discussion of which is better, OSPF or ISIS, or which is better, running an IGP only or running MPLS only, because that's a rat hole. Okay. Now, in a prior NANOG, there was something, this is actually good that this comes up on a slide, because Dave Katz is notorious for showing up for NANOG with no slides, and sometimes, he actually had slides this time, which is, let's hear for Dave. He had slides. At a past NANOG, he just kind of showed up, and he really covered some good material, but he just wrote things on a transparency and waved his arms a lot, but he made a lot of sense. And I'm calling this the Katz effect, and we've always referred to this as something that Dave Katz pointed out. There was, an internet service provider that did do a full mesh of on the order of hundreds of routers in a full mesh over ATM, and they discovered that it didn't work. And the reason initially was thought to be that there was a scaling problem with the SPF, but Dave corrected us, and that because Dave was the one that was working directly on the problem, because at that time he was at Cisco, and working on the IGPs at Cisco, and he explained that it was really a flooding problem. If you have one link go down, two routers announce one LSA. If it were OSPF, it would be one LSA. If it's ISIS, it's one LSP fragment. So two LSP fragments go out to each of the neighbors of those two routers. So you have 2 times N propagation. And then each of those routers that receives that LSA sends that same LSA to each of its neighbors. So you have in the network a total of N squared, 2N squared LSAs, and each router receives 1 times N squared. If a router goes down, everybody that's adjacent to that router, all N routers that are adjacent to that router, originate an LSA, send it to everybody that they're adjacent to. They all resend it to everybody that they're adjacent to because they're not sure that they know it. And you have each router receives N squared, or in this case, if it's the number that you're adjacent to, A squared LSAs. Now, if it's an LSP fragment and it's the size of a full NTU, that's 4K for typical NTUs. If you have on the order of 1,000 routers, N squared times 4K for each LSPDU fragment is on the order of 40 megabytes of UDP buffering that you would need to be able to absorb that without dropping anything. And most routers, at least at that time, no router would be able to dedicate 40 megabytes to UDP buffering for the IGP. And even now, that's kind of a lot. So, and there's also a fair amount of processing. Okay. Now, scaling the IGP, I'm just going to use John Moy's estimate. There are arguments about whether or not this is accurate, but John Moy estimates that the SPF, if you sort the links, is L log 2 of N for L links and N nodes. The incremental SPF is much faster than this. And packet designs, Jengas in particular, have been advocating using an incremental SPF. It does help quite a lot. I'll go in later. Well, I'm actually not going to discuss, I'm not going to try to quantify how much better an incremental SPF is than a full SPF. But in large topologies, you can save at least a factor of 10. And sometimes better. However, there are cases in which the link that fails is very close to you, and it affects, it can sometimes affect the entire topology. In that case, the incremental SPF can actually be slower. Okay. The obvious question then, though, is if flooding is fast and the full SPF is very fast, where very fast, even the slower, even a very slow full SPF would be a half a second or a second, an extremely slow SPF, then why does it take 3 minutes for some routers to recover? And the obvious answer, which I think has been covered by others, is that route install dominates. Packets don't stop dropping just because the SPF is complete. There are a number of solutions to the route install problem. Dave mentioned one of them, which is use a two-stage route lookup. The obvious one, of course, is to just improve the time, the transfer time from the route processor to the forwarding cards, and the time it takes to actually install in the ASIC routing tables. That would get you, if it got you a factor of 5, it got you a factor of 10, still wouldn't be enough. The convergence would still be way too slow for something on the order of 250K routes. If you do a two-stage lookup, though, if you had 250,000 BGP destinations, those would map into however many destinations you had in your IGP. So if you had say 1,000 nodes and a total of 10,000 destinations, you've at least reduced that to 10,000 entries that you have to change. Your ASICs have to be capable of doing a two-stage lookup, and some are and some aren't. If you do have the spare cycles to do a two-stage lookup, in this case you would save a factor of 25 right off the bat. The case where you don't actually save anything is if the BGP route would change because the IGP cost has changed, because that's part of the BGP lookup. In that case, if you changed all the IGP routes, you then still have to go through the BGP table, but if only 20% of those routes changed because the IGP costs changed, then you still have a savings. You can either map to, there's 1,000 nodes, so you can either map to a node, or you can map to all the destinations. Some of the ASICs have some limited table space, so if you wanted to map to all of the destinations, you might run out of table space if someone were to inject all of BGP into their IGP, for example, and you wouldn't want to have some sort of a catastrophic failure. So if you map to the number of nodes, you wouldn't have that kind of catastrophic failure. And you could also have a three-stage lookup, although I don't know that anybody has enough time in their ASICs to even consider that. I know that we don't. Or I don't think we do anyway. We have a fair amount of time, but yeah. If you do a two-stage lookup and the IGP, and you don't have BGP routes changing because the IGP costs change, sub-second route install is achievable. And we know that because, well, it's achievable. We know that from testing. SPF requires, MPLS has some different requirements for scaling, and the main difference with MPLS is that you can potentially have one constrained SPF per label switch path. If you have, say, a 100 node core and your ingress for 100 LSPs and a link breaks, you could potentially, if you had to reroute, say, 40 LSPs, you could potentially have to do 40 CSPFs. If your CSPF was very slow, say a half a second, that would be a very significant amount of time. Even at a 100 millisecond SPF, that's a significant amount of time. 4 seconds is longer than most people, or if you need 4 seconds of computation, it's going to take a little bit longer to get all the routes installed, and people are typically looking for a faster convergence than on the order of 5 to 10 seconds. There are ways of getting around doing the CSPF, and I'm going to discuss those in a little bit. Scaling the route install in MPLS is, in many cases, easier to deal with because in MPLS you have the ability to configure a cost on the LSP, regardless of the route it takes. And if you take advantage of that, then you never have a BGP route change because the IGP costs changed. If you have non-MPLS routers, one of the designs is to have a flat IGP, but have a limited set of those routers in the core being MPLS capable. You then have, if you have the ability to advertise the LSPs, the MPLS LSPs, into the IGP as if they were links at a fixed cost, then the routers around the edge don't see any change in the IGP when a LSP reroutes. If you have routers on the edge that take 3 minutes to switch over the BGP routes, you avoid having those routers do any work. Okay. Two-stage lookup is common. I'm not sure, but I think everybody does a two-stage lookup. If you have on the order of 100 MPLS tunnels and you have to change 40 of them, you have to change 40 table entries in hardware. So it's route install is not a big issue for MPLS as long as you have the two-stage lookup. If you had to change to 250,000 routes in order to accomplish a reroute, then route install would be a significant problem. I don't think that is a problem for any implementation now. Okay. MPLS, of course, offers some fast recovery techniques. Fast reroute, I think everybody's implementation is well, the implementations vary, but I think all the implementations are way sub-second. And some of the implementations, even with large numbers of LSPs, consistently come in under 50 milliseconds, well under 50 milliseconds for the fault recovery. Of course, the benefit of fast reroute is that you are recovering from the fault at the point of local repair. Wherever the SONET detect, as soon as the SONET detect has occurred, it's a local issue making the repair. Those routers that do things quickly have all of the state pre-installed in all the forwarding cards such that, and at least some of the implementations don't even involve the route processor. The forwarding cards communicate directly to accomplish the repair. And that's how you can consistently get well under the 50 millisecond mark. The disadvantage of fast reroute is you have a lot of detours. You have a lot of LSP state in the network. Another technique which involves pre-signaling a backup path is to use a standby LSP. And a standby LSP is just a second LSP from the ingress to the egress that doesn't share any resource. And that's where shared SRLGs, shared risk link groups, come in handy. So that if you have two links which from the standpoint of the topology are unique, however they share some resource, whether it's they're both lambdas on the same fiber or whether they share some other resource, down to they might be fibers in the same conduit. If there's some chance that they're going to fail together, you can put them in an SRLG and then avoid trying to put the backup path over a link that is going to fail at the same time as the primary path is, which makes then the standbys effective. But standbys, since they're pre-signaled, don't require that you do any SPF before the recovery. It's simply send the message back to the ingress, and the ingress can then, and they're typically sub-second recovery. The ingress simply switches over to an already signaled LSP. Pre-computed LSPs are another option where you compute the path but don't signal it. The disadvantage of pre-computed alternate paths is you then have you have a fair amount of signaling, plus you can't do any traffic engineering on the backup paths if you don't signal them. So if you do dedicate bandwidth to the backup LSPs, and to the standby LSPs, and there's a way of doing that without actually interfering with your primary LSPs. You simply put it on a different holding and reserving priority. If your primary LSPs ignore the other holding and reserving priority, then it's as if the standbys weren't there, and the standbys have to take into consideration when they're routed the bandwidth used by the primaries, and in addition the bandwidth used by the other standbys. So you get traffic engineering, so you get a reasonable initial state on the recovery, sub-second recovery, very low congestion after the recovery, and then you can get further optimization after that when you reroute the primaries. Okay. When an IGP only network, when you have using IGP only, the recovery takes a number of steps. The advertisements are originated by the routers that detect the fault. So there's detection, origination of the LSAs. The LSAs are flooded. There's only one SPF required per router, as opposed to MPLS, where there may be many SPFs required for each router. So the SPF, if the SPF time is 100 milliseconds, it's only 100 milliseconds times 1. The IGP routes are installed, and at that point, if you have a two-stage forwarding lookup, that's when your recovery occurs. The point where IGP routes are installed is typically sub-second. Okay. At that point, you map BGP routes onto the IGP routes, and then BGP routes are installed. So if you have a two-stage lookup, then you may have some routes which require that the BGP entry be changed, and you would get your recovery at that point. But if it's only 20% of the routes, at least you'll save a factor of 5. If you have to install 100% of the affected routes because you don't have a two-stage lookup, that's where you start to get your very long install times. Okay. With MPLS, as soon as a fault is detected, or within implementation dependent, but within 10 milliseconds on some implementations of when the fault is detected, the fast reroute recovery can occur. After that, advertisements are originated. The fault detection, and in a good implementation, the fault detection does not require any attention of the route processor. Advertisements are typically originated, or typically have to go through the route processor. Some routers have put the adjacency, the IGP adjacency processing on the line cards, and that takes decoupling that from the route processor allows you to decrease your timers without minimizing the risk of causing any instability, because typically the processors that are on the forwarding cards don't have any long threads of execution like SPFs. Up to one SPF is required per MPLS LSP. However, there are ways of avoiding that, and that's going to be a little later on. The new MPLS LSPs are signaled, and then when, by the way, I missed a step here. After the flooding, the ingress notices that the LSP that it's currently sending traffic on is infeasible. If it already has signaled an LSP, it can then very quickly send information down to the ingress cards to simply switch a table entry. And if there were, for example, 50,000 routes which all use the same table entry, you change to one table entry and all 50,000 routes go over to the standby LSP. So that's something that can be done relatively quickly, and typically that's sub-second. Here you have the flooding time. You have to contact the route processor. The route processor has to send something to the line cards, but the amount of work that's done is very small. So this is typically sub-second. Then SPFs are done. There may be many SPFs. LSPs are signaled. There's signaling delay because you've got to send path messages, get the RESVs back. And then when signaling is complete, if you didn't have any kind of a standby or fast reroute, that's when recovery would occur. In some implementation, well, here it varies again tremendously, and it varies based on the topology and the implementation. Small topologies, good implementation, you may be talking about a couple of seconds. Very large topologies and very poor implementations, you could be talking about a couple minutes. If you did something like full mesh on a very large network, you could be talking about an enormous amount of time, and I'll go into that later. However, after this initial signaling, then if you had backup LSPs, you then have to reestablish the backup LSPs. Whatever fast reroute LSPs you had, if there's a new primary path, they're no longer applicable, you have to resignal those. If you had a standby and you rerouted the primary and the standby may now be sharing a link, so you have to reroute the standby. And then there may be some optimization done, because after you lay out all the primary paths, if 5 different routers had to lay out primary paths, they may all use the same resources, depending on how fast your feedback is relative to how fast you're setting up your LSPs. You may have overutilized some resources in the network, and you may decide to further optimize. This is where the MPLS adaptivity stuff comes in. And this is done with make before break, so there is a jitter, there's a discontinuity and delay, but there should be no loss. And then after any optimizations, you then have to, again, establish new backups. Okay. The things that can be done to improve scaling fall into 2 categories. Things that the ISPs can do, which is change the network topology, and things which the router vendors can do, which is router implementation things. Okay. So now we start to try to roughly quantify the impact of topology. This is what the ISP could do to either make things really bad or to improve things. If you want to make things really bad, you take a really big network and you build a full mesh. The IGP flooding, if you have a link down, each router will get 2,000 LSAs or LSPDU fragments. If you have a router down, actually, that's correct. You should have about 1 million fragments, LSPDU fragments, which again I said, 40 megabytes of UDP buffering if you really wanted to make sure that you didn't drop any of those. And plus a lot of processing. It's not likely that that's going to happen very quickly, and this was actually a cause of problem in the circa 1995 time for some ISPs. If you build a single area network and you use a partial mesh, and here I just use 10 links per router. If you use a number of, that's actually not an unreasonable number. Some of the older networks were 4 or 5 links per router. 10's actually not that far off. Some are more mesh than that, some are less mesh than that. If you get a link down, I think that should be 20, but 20 LSPDU fragments is really not an issue at all. If you get a router down, you should see 100, and that also is typically not a problem. Another design, which you saw in the IP over ATM core days, was a full mesh within a core area or a core region. Well, actually, the old UNet global crossing design was to have a single one area IGP, but have a set of core routers with a full mesh of, or the dual plane design, which is a near full mesh of VCs between those core routers, but there were a very small number of core routers. Here I use the number 100, but if you had a link down, you would get on the order of 200 LSPDU fragments, which is a manageable number. If you had a router down, you still get a large number, 10,000 LSPDU fragments. Some of those networks had on the order of 30 or 40, so you don't get quite that large of a number, but it's enough. It was enough to still cause some trouble for the IGP. And this is one of the things that have given IGPs a bad name. And in my opinion, it was really kind of a bad design. If you have a partial mesh, which would be like an IGP-only network, as opposed to a something like IP over ATM, you would get on the order of 20 and 100. That should be 20. So why would anybody do a full mesh? And the answer is really people are interested now in doing it with optical and TDM, and there's no interest in doing a full mesh over ATM. But those who believe in optical switching or an all optical core want routers around the edge of this core, and they would be exhaustively connected through that optical network. And the full mesh in a core area again becomes of interest or of concern. And then you could eliminate that full mesh if you're running GMPLS on optical switches. But we won't go down that path too far, because opening up a discussion of the relative merits of GMPLS would be opening a can of worms in this case. The impact on the IGP SPF, well, again, going back to John Moy's estimate that it's L log 2 of N. If you have a full mesh, then L, the number of links, is on the order of N squared. So if you have N links, then you have the SPF computation is N squared log 2 of N. If you had a partial mesh and there are 10 links per router, L would be 10 times N. So you would have 10N log 2 of N. And these low-level operations, you would have, in the first case, 10 to the 7th of those low-level operations, and in the other case, you would have 10 to the 5th. So it's quite clear that you've gained a factor of 100 by not having full mesh. And just doing a sanity check, if that low-level operation took 1 microsecond, you would get, for 10 to the 5th, you would get 100 milliseconds, which is on the order of what some of the IGP SPFs yield. Now, if you have a small SPF, it turns out that this will be less accurate at predicting how fast your SPF is. But if you have a small area, you're typically not even concerned about how long the SPF takes. And here, I did mention that an incremental SPF, in the worst case, takes as long, if not longer, than a full SPF. So it is a concern that in some of these cases the numbers can be fairly large. It's not a concern for the IGP, though. It's a concern when you have to do many more of these. Well, again, another example is if you have a partial mesh with 10 links per router and you only have 100 routers in the area, you have a 7 millisecond SPF, and that's really of no consequence. Okay. Now with the CSPFs, if you have a full mesh and you're trying to connect every router in your network to every other router, all the way out to the edges, and you have 1,000 nodes, that means that every router potentially could have to do 1,000 CSPFs. That would be if every single one of them were affected. If you have 2 links from a router that's near the edge and you have to reroute half of your LSPs, that's still a large number. If you have to reroute 500 LSPs. If you did have to do 1 CSPF for each one of these, then what you end up with a full mesh with an n cubed log squared of n problem. And if n is 1,000, you have something that's on the order of 10 to the 10th. So if you figure that out, if you had the same sort of efficiency in your SPF, that would be 2 hours and 46 minutes worth of CSPF computations. So yeah, that looks like we got a bit of a problem there, so don't do that. Now, it's really interesting that in the early days of MPLS, we had Tony Lee standing up and saying, oh yes, we need 40, 50,000 LSPs, traffic engineered LSPs, and well, there might have been a reason why no one's actually done that. Okay, if you have a partial mesh, it's on the order of 10 to the 8th. Even that, 100 seconds, that's still a very long time. If you have just a core area, if it's a true area network, you have on the order of 7 times 10 to the 6th, which is not really that much better if you had a full mesh, like the optical core idea with MPLS in the optical core, if you had to do that many CSPS. If you had a partial mesh, and that would be, you could do that if you didn't have an optical core where you were trying to do a full mesh, or if you had GMPLS, then you have 7 times 10 to the 5th, which is actually a manageable number. You'd have 700 milliseconds, or not quite a second worth of CSPS, and that's actually a manageable number. That would be if the implementation just did CSPS every time it had to reroute an LSP. There are a couple more complications. After an LSP is rerouted and you need to think about whether there's a better way to route that LSP, a good example is if you have 2 different ways to get from A to B, and one of the ways you have 90 milliseconds of LSPs routed on there, and the other ways you have 80, and you're considering rerouting an LSP. Well, if that LSP is taking 90 megabits on one and 80 on the other, and that LSP is taking up 40 megabits, and you move it from 90 to the one with 90 to the one with 80, you now have 50 and 120. So you have to take into consideration the amount of bandwidth that that LSP is using. So if you have a map of the topology, you take the existing path of the LSP, and every link that that LSP currently uses, you have to subtract the bandwidth of that LSP from that link before you run the SPF. So that means that that SPF is unique. No other LSP is going to use exactly that SPF, although when you're doing this, all of the LSPs that you're considering rerouting start from that base and have a very small amount of change from that base. So this is a very good candidate for an incremental SPF. Everybody starts out with the same SPF, makes some changes to a very small portion of the topology, then you have to run an SPF, so an incremental SPF makes sense for that situation. Another case is when you're doing fast reroute or you're doing a standby. The standby, we'll just take standby as an example, can't take any of the same links that the primary is taking. And if you're using SRLGs, it can't take any link that shares an SRLG with any link that the primary is taking. So you have a similar operation where you start out with the SPF, with the same base SPF. You go through the hops that the primary takes. You look up all the SRLGs for each link, and then you mark each of the links which share an SRLG in the topology, and then this is another candidate for an incremental SPF. At that point, you rerun an SPF, incremental will be faster, and you determine the best path for your backup. So both of these are candidates for incremental. I was mainly talking there about things that you could do in the network topology. That last slide here went into a little bit about CSPF, but prior to that, it was really all things that you could do in the network topology which have an impact on scaling, both for using an IGP only and if you're using MPLS. And we also looked at the fact that the number of CSPS and the amount of CPU time that you could consume with MPLS starts to get into scary numbers, even though Dave just told us that the SPF is never scary. 2 hours of computation would be a very scary number. So some of the things that you can do from the implementation standpoint, in terms of the IGP scaling, the flooding scaling, mesh groups help. I think this should have said flooding scaling. Okay. No, it's IGP scaling. And then it was pointed out by Packet Design, it was also pointed out in the tutorial last night that giving priority to reflooding over the IGP SPF it makes a very remarkable difference. That was also in the spec too for, I think, OSPF, but and maybe ISS, but some implementations already did this, but the observation was made that doing it the other way is wrong. The incremental SPF helps, and there, in the work that we've done, we've typically seen like a factor of 10 in improvement on average. Decoupling the IGP from BGP processing can help. There, what I mean is putting the IGP adjacency processing, for example, on the line cards. That's what I mean by decoupling it. Putting it on another processor helps. Also, any software techniques for decoupling it, being able to use the scheduling capabilities of an operating system so that you don't run, if you have 100 millisecond SPF and you have very short IGP timers for GigE, for example, you don't become unstable as a result of the route processor having some computationally intensive things to do, long execution threads. So the more you can decouple that hello processing, the better. Improving route install is probably the biggest thing that can be done to improve IGP scaling. And the 2 or 3 stage lookup is the big benefit there, if you can do a 2-stage lookup. For the MPLS scaling, the best way, well, anyway, there are 2 ways that you can approach the problem of CSPS being slow, and one way is to just try to make it as fast as possible, and we were looking at very long times in terms of the total amount of CSPF you had to do. So if you got a factor of 10, that may not be enough. So trying to make it as fast as possible in itself may not be the right approach. And an alternate approach is to try to avoid doing a CSPF at all, if at all possible. And one way of doing that is to cache the results. If you have an underutilized network and you do a CSPF, well, for one thing, is if you typically only have a certain limited number of color constraints on your LSPs. You have different types of services, and in many networks, there's only one. They either don't use colors at all, or they have maybe 2 or 3 different sets of color constraints, color and holding and setup priority constraints. Beyond that, they have different bandwidth constraints. They may have some LSPs which have identical bandwidth constraints, but if the network is very underutilized, it doesn't matter what the bandwidth constraint is, whether it's 10 megabits or whether the LSP requires a gigabit. If you have 8 gigabits available, they're both going to fit on the same path. So often in caching, so caching has a big benefit. And there are two things that you can do. One is you can cache. If you have to apply constraints to 10,000 links, if you have 2 LSPs with identical set of constraints, you essentially don't have to do anything. You can just simply apply the same link set. If you were to apply the constraints again, you'd get the same result. So you can cache those link sets. If you have 2 LSPs which differ only in bandwidth, you can just simply quickly run through the link set, and you run through the rejected links if the old LSP had a higher bandwidth constraint, and you run through the set of links that were available if the old LSP had a lower bandwidth constraint. And you simply just run the bandwidth constraint only, which if very few links change, it's a very small amount of work. If no links change, it's no work. You just simply do a check, and then you decide that you can use the same link set. If you're doing any kind of dynamic allocation here, the big savings is that you don't have to allocate any data structures, and that the dynamic allocation is probably the if you do wherever you do dynamic allocation, that's usually the limiting factor. That's usually what the biggest contributor to the small low-level operations. The other thing you can do is you can cache the SPF results. Now, link sets are typically very, very small data structures. Well, the information as to whether a link is available or not can be stored in an extremely tiny data structure. A complete SPF result is many data structures, and it's a fair amount of storage, so you don't want to store too many of those, but the limit to the number that you have to store is the number of LSPs. If you were to store one SPF result for every LSPs, which would be a pathologic case, you'd be consuming quite a lot of memory, but at least it's bounded. Okay. And the other thing is, of course, to use the incremental SPF where applicable. I don't want to go too much into the algorithms that are used here, that can be used here, but if you have two LSPs with similar constraints, they differ in bandwidth, and the difference between the two link sets is only a handful of links, this is another case where an incremental SPF has a tremendous benefit. So in looking, if you have the link set cache, you find something that, you find constraints that are similar, you then determine the deltas, you then go find the SPF, you can do an incremental SPF, and you can save a lot of work. So the idea is to avoid doing full SPFs wherever possible, and to do an incremental SPF if you can, and if you can, don't do any SPF at all. Try to find an existing result that exactly matches. And this next slide just briefly describes what would typically happen. I have 10 minutes left? Oh my God. I thought I'd never run this through in an hour. Okay. So briefly what you do is you find the entry in a link set cache. You look that up based on constraints. You apply the constraints, find the differences, look up the CSPF result for the old set of links, do an incremental SPF, and then cache that new result. Then if you're going to create a CSPF result that you know is unique, and it would be unique if you're going to apply some disjointness thing, or it's going to be unique if you have to compensate for the existing path if you're rerouting, then you don't actually try to cache that because it's just going to waste memory. Okay. See, I think I've pointed out some of these observations. If the constraints are identical, you essentially have no work. You look up an existing link set based on the link set, and if you compute a digest on the link set, you can just look up the digest, and you have very near zero work. You look up the link set, you look up the CSPF with the same digest. You actually, if you want to be safe, you run through and run a check on the links, and then you use that SPF result. It's already done. If the constraints differ only in bandwidth, but the network's underutilized, the deltas are null. If feedback hasn't arrived, for instance, if you set up a whole bunch of LSPs and a bunch of other routers set up a whole bunch of LSPs, but feedback hasn't come because you're doing this very fast, the set of updates that you've received is a null set since that link failure. If you did receive any updates, in other words, some of the links changed their bandwidth constraints, you can simply create a queue, and you look back from the most recent change to the point at which, like if you have an old link set, you computed that like a while ago, and it has a timestamp on it. You look back through the queue of things that have changed back to that timestamp, and you just have to change those links and no other links. So you can get a small set of deltas. Some of those may not change at all, but there are very few links that you then have to apply constraints on. You don't have to go through the whole 10,000 link set. 100 times if you have 100 LSPs, 1,000 times if you have 1,000 LSPs. 10,000 links times going through it 1,000 times gets to be a very large number. We tried to simulate this for, well, we did simulate this for customers, and I put trying there because there's limitations to what you can do with simulations. We found that the cache hit rates were extremely high. In many cases, we did one full CSPF, and then incrementals after that. In some cases, we did really just one SPF, and we were able to reuse it. It all depended on what, things like utilization and whether we took into account the feedback. And if you do the caching, if you do a really good job on the caching, then the performance actually becomes limited by your link set processing, because you're doing so few SPFs that it's going through those 10,000 or not going through those 10,000 links and applying constraints. It takes longer than looking things up in the CSPF cache and finding them, or looking things up and doing an incremental. There's an interesting observation that the link set processing becomes significant in terms of time. The alternate approach is, of course, to try to make the SPF faster. Now, one of the things that happens is if you need to save the SPF result, you need to do some sort of dynamic allocation while you're doing the SPF. That dynamic allocation makes the SPF itself slower. If you don't have to do any dynamic allocation, for example, if your nodes and links are going to be used exactly once, you can include some extra, data structure on the nodes and links themselves, which are used for the SPF and discarded after the SPF is used. But that means that you cannot reuse the SPF later. You can only if you do an incremental, you can only use the previously computed SPF result. You can't use one that was 5 results ago. You can get a little tricky with that. We considered doing this. We didn't actually do this. Sorting the LSPs according to constraints such that your incrementals were likely to be as efficient as possible. We discarded this idea. I got 2 more slides, Susan, so I'm okay. We decided not to do this, but it is a viable thing. If you were to get rid of all the dynamic allocation, you can make that low-level operation much faster. I have the point down here that if you wanted to do dynamic allocation and you wanted unlimited multipath, if you had limited multipath, like you said, I only want to be able to do 4 links, 4 paths of multipath from the IGP, for example, or I wanted to only consider 4 possible paths for MPLS if I was going to reuse something for incrementals. You could use a static allocation and you wouldn't have to do any dynamic allocation. If you wanted to not limit the number of multipath paths, you would have to have a dynamic allocation. I think that's a minor point. You could argue that that's not necessary. So then there's another issue, which always comes up in terms of scaling MPLS, which is hierarchical LSPs. And the question that always comes up with hierarchical LSPs is what are they for? Why bother? And scaling is one of the issues. Now, areas, if you already have broken up your network into areas, that provides very good scaling, and you can see that the numbers, even if you did full SPS, the convergence times that you could expect, the amount of computation that you need to put into the SPF is very small, even for the MPLS case. So if your core area started to get really big, you could use hierarchical LSPs to get more scaling, to get better scaling. And my question down here was, is anybody that big yet? And it's a rhetorical question because the answer is really no. Nobody has a 400 node core area in a 40,000 node network at this point, at least that I'm aware of. So nobody's that big that the scaling is the reason for deploying hierarchical LSPs. Then another reason that's often cited is LSP hierarchy can give you end-to-end LSPs, traffic engineered LSPs. But for the most part, people are using LDP for that. If they want end-to-end end-to-end LSPs, so that they can run their VPN stuff, they use LDP or any of their tunneling things. They use LDP on top of traffic engineering in the region or traffic engineering in the core. And the argument that seems to hold some water at this point is that if you want to support optical and optical TDM technologies, that the hierarchical LSPs are necessary, and this is really the motivation behind the GMPLS work. And I put down there, assuming someone wants that, but typically, well, I don't really see anybody doing that in the core, but that seems to be done. There's much more interest in that right now in the optical TDM kind of stuff in the edge technologies. So the assumption that someone wants that, I think, is valid now, but it's more on the edge. And is it a technology ahead of its time? No, I don't really think so. I think it's something that we have to pay attention to, because although it's not a hot deployment item right now, it will come in handy for the scaling longer term, and it is needed to integrate these optical and optical TDM technologies. Okay, conclusions. This is where I put Ed's little quote here, which is somewhat not applicable, which is we need something technical to make it a NANOG. It has to be some wild technical thing. So this is as close, I think, as we get to this NANOG. I tried not to get too much into algorithms and keep things as non-commercial as possible. No charts of this is what our router does. I may go into much more detail. I've talked to Jabari about presenting at the MPLS conference, which I guess is badly scheduled because it's at the same time as the next NANOG, but I may be doing, if anybody's interested in algorithms, I may be talking about that in much more detail and providing some simulation and test results there. I'm done.
We probably have time for a question or two if anyone has any questions.
No questions. I bored everyone to sleep. Okay.
Actually, I did have one question. Can you go back to slide 7? I was curious about the assumption that you, maybe it's not on this slide, but you said that you assumed that the MTU was 4K in the calculations. It wouldn't be a full MTU, right?
Well, people have typically used, people have typically used 4K, like ATM, the MTUs, 9180 or whatever it is. But that's been a typical assumption. And even on the GigE, no one that I'm aware of is using the 1500 MTU. It's typically using a larger MTU. But if it was larger, if it was a 9K MTU, then you would need 90 megabytes of UDP buffering, which would be even worse. Are you arguing that it should be bigger or smaller?
As a multiplier, it strikes me that using the assumption that the MTU is completely full to multiply times your model here, that seemed like too large of a number. Maybe the LSAs don't fill up the full MTU.
For OSPF, that would definitely be the case, because for OSPF you just send the LSA, and if there's only 2 LSAs to be updated, you would just send those 2 LSAs. For ISIS, if you've nearly filled the fragment, the LSPDU fragment, and you change something in the fragment, you have to send the whole fragment, and that's where that comes from.
Other questions? Great, thanks a lot, Curtis.